Okay, so today we'll discuss about the instruction set architecture and memory concepts. Okay, so in the third chapter, we'll study about one of the new assembly language processor that is called as a Spark processor. Okay, the instruction set architecture. So in that, there is a one type of a RISC computer. Okay, ARC computer we call it as a RISC and CISC. There are two the architecture of these are the computer architecture types. Okay, RISC, reduced instruction set architecture, and complex instruction set computer architecture. So ARC, a RISC computer. Oh, okay. So it is a type of a RISC type of computer architecture. We'll discuss that in detail. Okay, so for this you are required to refer the this particular textbook, that is computer organization by this one, John P. Hayes. Not one, this one, Mudoka. Okay, Mudoka Turing. This one, the first one. Okay, Miles Mudoka and Vincent. So that is the textbook that you have to refer. Okay, the PPT you will get. Okay, the you will get in the internet if you search with the that author name and this computer organization and architecture. Okay, so mainly here we'll discuss about what are the different hardware component of instruction set architecture. ISA, instruction set architecture, then a RISC computer, pseudo operations, synthetic instructions, and example of some assembly language program. Okay, and addressing modes and all we'll discuss. Okay, so in the previous lecture we discussed about the various data representation methods, floating point method, fixed point method, and the algorithms, multiplication algorithms, division algorithms, and all. Okay, that is a the second chapter. It is all about the data representation, and third chapter we discuss about a RISC type of processor, the assembly 32-bit assembly language processor. Okay, as you people are gone through the 8086 processor, right? So similar to that, here we will discuss about the this particular ARC processor. So you already know instruction set architecture. Okay, ISC means is consider a set of instructions. Instruction set architecture view of a machine that corresponds to machine and assembly language levels. Okay, each architecture, the computer architecture is having their own instruction set. For example, 8085, the instruction sets are different. Okay, and 8086 microprocessor is having their own instruction set. So likewise, each processor is having their own instruction set. Okay, that corresponds to the machine and the assembly language levels. A compiler, it translates high level language like English like statement, high level language which is architecture independent, into the assembly language, which is architecture dependent. Assembly language is architecture dependent. Assembler translates assembly language program into the executable binary code. Means, for example, move a comma b 8085 instruction. So this particular instruction assembly language program into corresponding binary code. It corresponds to, okay. So you have to refer the chart to, for each instruction there is a corresponding binary code. Okay. So for fully compiled language like C, Fortran, the binary codes are executed directly by the target machine. So Java stops the translation at the bytecode level, and JVM, Java Virtual Machine, the JVM architecture, which is assembly language level, interprets the bytes code. Okay. So I think you know the Java Virtual Machine Engine, okay, architecture. So it in which the Java bytecodes are executed directly. Java virtual machine where the Java codes are executed directly. Okay, the just you keep in mind the computer architecture is having their own instruction set. Okay, each microprocessor or each processor is having their own instruction set. It is a machine dependent. Okay, machine dependent. The system bus model of a computer system bus model. Okay, system bus model means here you can see the data bus. Okay, the data bus, address bus, control bus. So these are the three system bus. Okay, these are called as system bus, and these data bus where it transfer the data. Okay, and address bus, it handles the address of the memory location, control signals like read, write. Okay, read operation, write operation, input, output. Okay, so control signals, address bus. So these are all these buses that handle their own specific operation, and these are all connected to the central processing unit, registers, arithmetic logic unit, memory, and input output. Okay, means there is a communication between all these buses, communication among the system bus. Okay, so this is a model, the general architecture. Okay, a compiled program is copied from the hard disk to the memory. The CPU reads the instruction. CPU reads the instructions and the data from the memory and execute the instruction and store the result back to the memory. I mean, suppose if there is an instruction add B. Okay, this is a 8085 instruction. Add B means what? It is add the content of accumulator plus content of B register, store the result in accumulator. This is the operation. Okay. So the CPU reads this is the instruction. CPU reads the instruction and the data from the memory. Means so this is the operation. Add instruction is there, and the data, the value that is stored in B register, A register. Okay, CPU reads the instructions. Instructions means add instruction. CPU read the instructions and data from the memory and execute the instruction. Okay, once execute means it perform the addition operation. Addition operation and store the result back to the memory. Add B means add the content of B register, content of A register, and store the result in A register. Okay, store the result in A register. Like so, here to perform this operation, addition operation, CPU it uses the ALU means arithmetic. ALU means it is a addition like the in our case it is addition operation. It uses the registers and control signals. Okay, so CPU reads the instruction. Okay, it performs the operation, okay, and it generates the output. So for that, this bus is required. The data flow from each data bus, address bus means it store the address of the instructions, which is the next instruction to be executed. There is program counter and all. Okay, so this is the general model, bus model of a computer system. And common data bytes, you already know the data bytes and the size of the data bytes as a bit. Bit means a single bit. Okay, single bit. Nibble means 4 bit register. Byte means 8 bit. One byte equal to 8 bit register. 16 bit means 8. 16 bit is also equivalent to 2 byte. So 1 byte means 8 bit. Okay. So 2 byte means 16 bit. 32 bit means 4 bytes. 4 byte, 1 byte means 8 bits, 1 byte, 2 byte, 3 byte, fourth byte. So total 32 bit. It is also equivalent to 4 byte. Then 64 bit, 128 bit requires, okay, the data representation. Then comes the concept of one of the concept, that is big endian and little endian format, means how store the data. Okay, so big endian and little endian. Okay, so here we'll study this big endian and little endian concept. So big endian and little endian are the terms that describe the order in which sequence of bytes are stored in the computer memory. Okay, sequence of bytes of data, bytes are stored in a computer memory. Okay, sequence of bytes, like I already told, byte means what? 8 bit. 1 byte is equivalent to 8 bit. So here the sequence of the bytes, okay, and in 8 bit how we represent in hexadecimal? In hexadecimal, okay, in hexadecimal, suppose here like 4A, okay, that is 01001010. So this is how we represent, like 4 bits in hexadecimal data representation. Okay, so just keep in mind, big endian and little endians, these are the terms that is used to describe how the data are stored. Okay, the sequence of data stored in a computer memory. Okay, so storing the words in a memory, how we can store the data. Okay, how we can store data in a memory. Okay, like stack operation, push operation and all, stack and queues. Okay, so we have defined a word means what? It's a 32 bit size, right? So this means same as it is equivalent to 4 bytes. 32 bit, it is equivalent to how many bytes? 4 bytes. So 1 byte means 8 bit. 1 byte into 8 bits. Sorry, 4 byte into 8 bit. I mean, that is equivalent to 32 bit, right? So big endian and little endian means how we can store the data. Okay. So 32 bits means 4 bytes. The integer single precision floating point numbers and the MIPS multi-purpose instruction, okay, are 32-bit long. And how can we store these values in the memory? Means you know that single precision floating point data. What is the size? Single precision floating point data. What is the size? 32 or 64 bit? 32 bit, right? Double precision. Double precision is 64 bit, the size, right? So how we can store this data? Okay, how we can store these values into the memory? After all, each memory address can store a single byte. Okay, means actually the computer, it stores the data in a byte. Okay, in byte by byte. Okay, byte by byte it stores the data. So here we can see one example. Okay. Okay, now we are storing the data in a memory. Okay, like for example, 32-bit data, single precision, 32 bit data is there, and how we can store? How we can store in a memory? How we can store it in a memory? That is by using the single precision and not single. It's by using the big endian and little endian format. So here we split 32-bit data into 4 bytes. For example, a 32-bit quantity written as, so this is the 90 A B 12 C D. This is a hexadecimal number, base 16. Okay, which is a hexadecimal number. Okay, this is a hexadecimal. How many digits are there? 4, 4, 8. So 8 into 4, 4 bits. It's a hexadecimal. Abhi hexadecimal 9 indicates what? 1001. Okay. So 8 digits are there. 8 into 4. One digit is equivalent to 4 bits. So 32 bits. Right. 8 into 4 is 32 bits. So 4 bytes. This is 1 byte, second byte, third byte, and fourth byte. Okay, where each byte requires the 2 hexadecimal digits. Now, with respect to that, okay, what is little endian? Little endian means you store the least significant byte in the smallest address. Okay, we have this data. Okay, we have this data. Okay, little endian. Little endian means what? This is a format, little endian and big endian means how we store the data in a memory. So little endian, what it's saying? It says, okay, first we'll go with big endian, then little endian. Big endian means you store the most significant byte in the smallest address. Most significant byte. Okay, most significant means this one, the most significant byte, MSB. This is the most significant byte, and this is the least significant byte, LSB. Okay, most significant byte. So what the big endian is saying, big endian says store the most significant byte at the lowest address. Suppose I have a memory address. Okay, 9000, 9001, 9002, 9003. I have a memory address. And what is the definition of the big endian? Where big endian means it stores the most significant byte in the smallest address. Okay. So in my case, this is the data. Okay, and in this particular data, the most significant byte is 90. Okay, so the most significant byte that stores in the lowest address. So here 9000, 9001, 9002, 9003. What is the lowest address? 9000. So in this particular lowest address, we store the most significant byte, that is 90. Then after that it comes AB. Then after that it comes 12. Then CD. Okay. So little endian is opposite. So here big endian में क्या हुआ था? Most significant byte we stored in the lowest address. Okay. I hope it is clear. Big endian means the most significant byte we stored in the least significant uh, smallest address. Okay, most significant at lowest address. And little endian means you store the least significant byte, LSB in the smallest address. So least significant LSB. What is the least significant byte? CD. Okay, in the lowest address. उसके बाद क्या आता है? 12. After that AB will come. After that 90 will come. Okay. I hope it is clear. Now, anyone just unmute. Anyone unmute will take one more 32-bit number. Yes, anyone unmute? Your class CR. Yes. Yes. Unmute. Yes, roll number 7. Can you unmute? Roll number 7.
Yes, sir.
Can you tell me one four 4-byte hexadecimal number? Hexadecimal number. 4 bytes. 4 byte means 32 bit. So one tell me a number of 4 bytes, like A, B. This is 1 byte. 92, 34, 1, 5. So how many 1 by 2, 3, 4? Okay. So total is how many? It's a 32 bit. Okay. In hexadecimal means 1 digit equal to 4 bit. कितने digit से 8? So कितना हुआ? 32 bit, right? Now in the little endian format, big endian format. Okay, big endian and little endian. And address. Now I'll take some address like 5000. That is lowest address. 5001, 5002, then 5003. So lowest address. What is the lowest address? Sorry, little endian means what? It stores the least significant byte in the lowest address. This is the least significant byte, and this is the most significant byte. So least significant byte stores in the lowest address. So 15 is stored in the 5000, then 34, then 92, then AB. And big endian format. What is the big endian? Where most significant data, most significant bit data that stores in the most significant byte that stores in the lowest address. So that is AB, 92, 34, and 15. Okay. So in this way, it stores the data. Okay, here we can see the definition once again. Big endian and little endian formats. So in a byte addressable machine, means it stores the data in a byte addressable machine. The smallest data that can be referenced in the memory is byte. Okay, the smallest data. So multi-byte words are stored as sequence of bytes, in which address of multi-byte word is same as the byte of the word that has lowest address. So multi-byte words are used in two choices of the order in which the data are stored. That is most significant byte, that is MSB. Most significant byte at lowest address is referred as big endian. Okay, big endian means what? The most significant byte here. The most significant byte that is stored at the lowest address. For example, here, if it is 9000, x plus 1 means 9001, 9002, 9003. Most significant data is stored at lower address. Okay, that is big endian. Little endian means what? Is at the lowest address. Means the least significant data, LSB data byte, that is stored in the lowest address. So here 9000, 9001. Okay, just keep in mind, least significant byte LSB, it stores in the lowest address, that is called as little endian. Most significant byte is stored at lowest address means that is big endian. Big endian. Okay, so that is about the big endian, little endian data format, the sequence of the data, how it stores. Okay, that is about the big endian and little endian format. Okay. So here this one hexadecimal. You know, this is a 1 byte, second, third byte, 4 byte, 5th byte. This is LSB, least significant byte, most significant byte. Okay, LSB and okay. So suppose I will take address. This is the memory address. Okay, little endian. Can anyone unmute and tell the answer? Little endian, big endian. Yes, roll number 7. So what is the little endian? What data is stored in the lowest address? Row number 7. Least significant Little Indian means what? Least significant byte.
LS
Which one?
A0. That is A0.
A0. Good. Then after that?
84.
Okay. Then what about big endian?
34.
Yeah, 34 and 10. What about big endian?
10.
10 means most significant byte that stores in the lowest address. So this is our lowest address. 10, then 34, 84 and 80. Okay, so this is about the Little Indian and Big Indian. Okay.